Okay, before we get into mean inference, talk about type errors. So any hypothesis test you do, whether it's proportions or means or variance or anything else, it's not a guarantee the hypothesis test was correct. There could be an error that might have happened, right? So there's basically one of four possibilities. If you reject the null hypothesis but was actually true, that's a problem because you shouldn't have done that. So that's a type 1 error. Okay. Um, so if alpha is 1%, then there's a 1% chance a type error will happen. If you reject the null hypothesis is false, that's the correct decision. If you do not reject the null hypothesis and it's true, that's the correct decision. But if you need to reject the null hypothesis, uh, when you when you do not need to reject the hypothesis is false, that's an incorrect decision, right? So typically you see this little box right here for type 1 and type 2 errors, basically. So type 1 is you rejected it, but you shouldn't have, and then in type 2 is you need to reject it, but you didn't, right? That's a type 2 error, so it's kind of like a false positive or false negative, I guess. Maybe that would be a good way to explain it. Okay. All right, so let's say we have one where it's about a defendant in a trial, basically, right? There's four possible outcomes in a trial that could happen. So if the defendant is innocent and is convicted, that's not good, right? Whoop, that didn't work. What's going on with the arrow? There it is. Right, that's a type 1 error. So that should not have been the case, right? Because basically the default is innocent, right? Because it's innocent until proven guilty. So in order to convict somebody, you had to have rejected the null hypothesis, basically. If the defendant is guilty and is convicted, that's what should happen, right? That is the correct decision. So you reject the null hypothesis, which is they're innocent, right? So if the defendant is innocent and is acquitted, okay, that's a correct decision. Okay, but the defendant is guilty and is acquitted, that's a bad decision, right? Which means you didn't reject the null hypothesis, which is they're innocent, but you should have, basically. Okay, so the null hypothesis is they're innocent, right, until proven guilty. So if you reject that, which means you found enough evidence, basically, to find the fact that they are actually guilty, meaning not innocent, right? So that's your four possible outcomes for a situation. So it doesn't mean it's a 50-50 chance whether your hypothesis test is right or not, because it all has to do with the alpha value that's picked, basically. Okay, so let's say that you, excuse me, bring a car for 5,000 mile service, right? To do regular service, and they may or may not find other things wrong with your car, and if they do, they may or may not fix them, right? So the first thing that could happen is the car is not in need of additional repairs, and the dealership does additional repairs, right? So that's a type 1 error because there was because basically the assumption is because you took it for service, you didn't say anything about it being broken. The null hypothesis is it's not broken. You're just doing service. So if you reject that, that means you need to have done service, right? So the fact that they did reject it, but it did not need it, that's a type 1 error. Versus you could have the car needs additional repairs, and the dealership does additional repairs. Okay, that's what should happen, right? You rejected the null hypothesis and you actually did it. That's what should happen. That's okay. And the car is not in need of additional repairs. And repairs. And the dealership does not do additional repairs. right? So basically you did not reject the null hypothesis, which is it doesn't need repairs, and you didn't do them. So that's what should happen. And then you have the car needs additional repairs, and the dealership does not do additional repairs, right? Which is bad because basically you should have rejected the null hypothesis, but you didn't. So as a result, you didn't do the repairs, right? So basically, your null hypothesis is the car is not broken, because that would be your assumption going in just for regular maintenance, right? So if you reject that, which means you found enough evidence, the car is broken, right? Which means you would have done repairs, right? Maybe they found a bad brake pads, broken shock, who knows, right? So we do a little box here. We'll make the little box. Don't mind the terrible art skills, right? So 1, 2, 3, 4, right? Alright, so this is a type 1 error. Oh, I don't know why I put that. Let's put an actual 1 here. Right, this is a type 2 error. Right, this is correct. This is correct. Right? Because essentially, the null hypothesis is either true or the null hypothesis is essentially false. Right? Because that's just, all right. So basically, not broken. Right? Because if the null hypothesis is true, the car is not broken. Otherwise, it is broken. Okay. So you're gonna, over here, you're going to reject the null hypothesis. And do not reject the null hypothesis, right? That's your 4 combinations. So you either fix it, right? Because if you reject it, that means you think it's broken. There, you fixed it, and therefore you do not fix it. Because if you do not reject the null hypothesis, that means you believe it's not broken, right? It's not broken, right? Okay. So you get, let's see, make this blue perhaps. Right? So if the car is in need of additional repairs, right? But the dealership does additional repairs, is not in need, that's a problem. Right? That's a type 1 error. If the car needs additional repairs and the dealership doesn't do the repairs, that's a type 2. The other combinations, those are fine. Okay? Okay. So alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. That's the probability of rejecting null hypothesis, right? When HO is true, and the probability of not rejecting null hypothesis when HO is false. Okay, so they're kind of interrelated. A little diagram here that kind of puts it together essentially as far as alpha and beta. That's why you see alpha, 1 minus alpha, beta, and 1 minus beta basically. Okay. All right, so we have here, give a null hypothesis. We want Frank's rock climbing equipment is safe. Frank thinks the equipment is dangerous when it is safe. Right? So basically it's a false positive, right? So he's rejecting the null hypothesis when he shouldn't have done that, right? It's a type 1 error. Versus Frank thinks the equipment is safe when it is dangerous, right? So he rejected the null hypothesis, saying it's safe. Oh no, he didn't reject. I'm sorry, he did not reject the null hypothesis when he should have. So that's a type 2 error, right? Okay, so alpha is the probability. So alpha and beta are always probabilities. Probability of the equipment probability the equipment may not be safe when it is actually safe. And the probability Frank thinks his equipment is safe when it is actually not safe. Okay, so again, keyword there's probability every time. No, I don't think I need the word of. Okay, now we have given the null hypothesis would be the blood cultures contain no traces of the pathogen. Okay, so you, oops, on the wrong thing. You detect the pathogen when it contains none or no pathogen. I guess that might be better. Don't. And versus you do not detect the pathogen when it contains pathogen. Right? So, false negative, right? False positive, correct? Type 1 error is false positive, false negative, right? So you detect it, but you shouldn't have false positive. You didn't reject it, but it is there. That's false negative, right? So the probability of you detecting the pathogen when it is not there, I guess. The probability. Why does that keep happening? The probability you do not detect the pathogen when the pathogen is there. Okay. So again, the key. Oh. All right. The key being there is these are probabilities, right? Okay. Because again, if we go back to here, you don't want alpha and beta, right? That's bad. That means you have an error, right? False positive, false negative. Okay. Let's see here. So the victim of an automobile accident is alive when they arrive at an emergency room of a hospital. The responders. These are kind of redundant. I'm just going to give you the answers to these. And we'll go from there. Just kind of save a little bit of time. And you can kind of look through them. Okay. So the victim of an automobile accident is alive when they arrive in an emergency room at a hospital. The responder thinks the victim is dead when they're alive, right? And the responder thinks the victim is alive when they are dead, right? Type 1, type 2 errors. Again, probability of these things happening. The patient is not sick, right? So basically the doctor thinks the patient is sick when they are not sick, so false positive. The doctor thinks the patient is not sick when they are sick, false negative, right? Probability of each of those happening. An experimental drug claims a success rate of at least 75% of males with prostate cancer. The patient believes the cure rate of the drug is less than 75% when it's actually at least 75%. And the patient believes the drug has a cure rate of at least 75% when the cure rate is less than 75%. So I just want to do a percentage one there, basically. Okay. So let's do a little picture here on this page 5. Okay. All right. So the null hypothesis is the percentage of adults with jobs is at least 88%. So do not so type 1 and type errors from the following statements. So is there a type 1 or type error? So if I think about this, not to reject the null hypothesis and the percentage of adults who have jobs is at least 88% when that percent is actually less than 88%. So that would be a type 2 error, correct? So you didn't reject it, right? That's the key when you should have. Here you didn't reject it, but that's what should have happened. That is the correct decision 3. Okay. You do reject, and that's what should have happened. Okay, so that is that's not what should have happened. The reject the null hypothesis and who jobs at least when that percentage is actually okay. So that's actually wrong. You rejected it wasn't that way. So that's a type 1 error, right? So it's a false positive because you rejected it and you shouldn't have. So if you rejected it and it was, that is the correct decision 2. Yes. Okay. So let's draw the picture here. Draw a little box. Box, right? So we have decision 1, which is bad. Decision 2 is good. Decision 3 is good. Decision 4 is bad, right? So that's a type 1 error. Type 2 error. This is correct. This is the correct decision, right? So null hypothesis is true. Null hypothesis is false, right? And then there's the question of what do we do? We either we rejected the null hypothesis, or we do not reject, or did not reject, whichever one you want to put. Reject the null hypothesis, right? Okay, so type 1 error was we rejected it, right? Which is right here, and rejected it. But it was true, so that's a problem, correct? And then up here, we did not reject, but it was false. That's this one right here, right? Because we didn't reject, but it was false. And what I mean by decision 3 is this is the decision 3 essentially, and decision 2 is decision 2 essentially. Okay? All right. So it's always one of those 4 outcomes, essentially, every hypothesis test. So basically, in inference, what you're supposed to understand is when you do a hypothesis test in confidence interval, it's never 100%. You're not sure, right? You're inferring as to what the answer should be. That's how statistics really works. Okay, so power is the 1 minus beta, basically. Okay. When you choose an alpha level, or you calculate the alpha level based on the number of samples, that is a type. So basically, you're setting the probability of type 1 error to alpha. So alpha is the probability of type 1. Thus, you pick a lower value for alpha. Okay, and Fisher, which is a guy who comes up a lot in this book or most stats books, is the guy who basically said the default alpha value is 5%, right? Well, he didn't say 5. He said 1 out of 20 is a good value, which is, of course, 5. So when it doesn't specify, that's what you use, essentially, by default for most books. Right? All right, so type 2 error is the null hypothesis is false, and you did not reject it, right? Which is a problem. So you need more power, and so there's many ways of increasing power, essentially, right? Which is the 1 minus beta. So you increase the sample size, which may or may not be possible, right? You may not be able to get any more. You increase the significance level, which is bad because if you want to lower the alpha, right? Because alpha is known as a significance level, which is which you typically see in the problems from last week and you'll see in this week. So the problem is it's kind of a balancing act between type 1 and type 2. That's why these things overlap here, right? Because if you increase one, you're decreasing the other and vice versa. So the effect size is the true proportion is further away from the null. The difference between the null hypothesis value and the true value of the model parameter, right? Because what we think it is and what it actually is, the distance between them is the effect size, essentially, which we don't truly know, right? Something you can really do is get more samples if you can, right? And then you can play around with this a little bit, but essentially that's why Fisher always said, you know, use this. We're not going to always use that, but nonetheless. Okay. So I get a little comparison here about sliding alpha, beta, and around as to what exactly happens. Okay. So basically, if you reduce the probability of type 1 error, you're basically going to increase the type 2 error, right? So there's not a win-win situation basically. Okay, that's what we're trying to get down to. One affects the other. Okay, can the power be directly calculated from alpha? No, it cannot be. Not with what we have so far. Okay, it cannot be basically. Okay, because power is 1 minus beta. Okay, but so essentially, right? No, you can't. So if I want my power, I just have to subtract this, right? So my power here would be what, 85%. The power here would be 70%. Okay. All right. If you reduce the value of alpha, what happens to the chance of a type 1 error? It goes down. And the type 2 error will go up. So again, if you reduce alpha, which is a good thing, right? So instead of going to the 5%, Fisher will go down to 1%. That'll help you with the type 1 errors. But then you increase your type 2 errors. So did you make any headway? Probably not. Which attribute do you control over between sample size, effect size, and significance level? Well, sample size you can control if you can get more samples. Effect, not so much. You don't have any control over that. Significance level, you kind of have a ability to change that, but it's not going to be a win-win type situation. Okay. Confidence intervals and hypothesis tests. A little video there if you want to watch that. I got some more videos in the first page too. So if you want to watch extra stuff, I got some right there. Where am I at here? Okay. If the hypothesis test rejects the null hypothesis at a given alpha level, then the corresponding confidence interval, if the hypothesis, okay, I know what we're doing. All right. So if you were, come on, if the hypothesis test, here's the key here. If you rejected the null hypothesis, it means you don't believe in it, right? So if you reject it, the confidence interval does not contain. Okay? If the hypothesis fails to reject null hypothesis, then it does contain the value essentially. So the hypothesis test and the confidence interval should line up basically. Okay? All right, and then the alpha levels change from one to the other too. So essentially, if it's a one-sided hypothesis test of alpha of 5%, then the confidence interval is 90%. Right? With alpha, can't draw alpha very well, of 0.10, right? Essentially, look at it this way. Here's my normal curve, which is god-awful. If I have a one-sided test, that's 0.05, right? If I do my hypothesis test, right? When I do my confidence interval, the confidence interval is two-sided. All confidence intervals that we do are two-sided. So there's another 0.05 over here. Hence why we get a 10% basically. Okay? So it's not the same alpha for both the hypothesis test and the confidence interval. Whoop. Okay, so let's say I have a two-sided hypothesis test, right? With alpha of 0.05, right? Which means I have 0.0, 0.025 here, and I have 0.025 here for my hypothesis test. And the confidence interval is going to be a 95% confidence interval, right, with an alpha of 5%, right? Because the hypothesis test was two-tail, and so was the confidence interval, right? Okay, so let's say I have a 95% confidence interval. Let's go the other way around now. 95% confidence interval with an alpha of this. Then what is the associated alpha for the one-sided hypothesis test, right? So, so that means this is 0.025, right? And this is the 0.025 because all of our confidence intervals are two-sided for these we've done so far, right? So the hypothesis test, the alpha is 0.025 because it says it's one-sided. So it's either this side or this side. I don't know which tail, if it's a left tail or right tail test. I don't know. But that's what it's going to be, right? Okay, so if it's a 95% confidence interval, okay, 95, so that's 0.025, and that's 0.025, right? Because again, confidence intervals, they're both two-tailed for us for what we're doing. But the hypothesis test is also two-tailed, so the hypothesis test, the alpha is also 0.05. I make terrible alphas. Okay. All right. All right, we'll do an example on the next page here in a second.